This is another video in the fundamentals of electrical circuits sequence, and here what we want to talk about is a couple of ideas that you may hear as you're working with changing signals that change with time. So if you look at a sine or a cosine signal, for example, let's say a sine signal will look like this. And if somebody wants to kind of get an approximation of how much voltage on the average is delivered, if you go with trying to understand equivalence to like a DC delivery from the signal, if you just take the average of it, you'll find out that this, let's say this was V of t, and this axis is t. If I average this, this is gonna be positive, and I'm gonna have an equivalent amount on the negative side. So if I average it over a period t, one period, the answer is gonna be that the average, a straight average of V of t is equal to 0. And this is a problem that's encountered by many different signals. They might have it to different extent, but they all do have it. For example, even if I had a sawtooth signal here, even if the lobes were not the same, the average really doesn't tell me if this amount of electrons were shipped in a DC format. What would it look like? So over time, they've decided a good way to talk about this is, let's go ahead and take these negative side and put it up on the positive side. And what is the best way to do that? By squaring it. So over time, we've come up with a way of talking about, if average where negative and positives are added together, if you wanted to convey that message of how much electricity or voltage or current is being delivered, we use something called root mean square value, or usually RMS. That's how you usually see it, value. Sometime you may also see this is referred to as the effective, because that's what effectively, if you were looking at the magnitude, this would be the effective value that is delivered. So sometimes call it RMS value and all that. So how do we do that? If somebody gives you a signal, let's say V of t, and they ask you to find an RMS value of that, you simply say, okay, V RMS is going to be equal to, just as the name says, root, okay? Mean means if I'm going to average it over one period, and I'm going to go over one period, this basically says you can start anytime as long as you stop after one whole period is completed. And then you square the signal, since V of t is basically Vm, if it was a sinusoidal, right? If it's not, just V of t squared and d of t. So that's a general form. And that's where it stops. And of course, if you wanted to write the I version of this, if let's say somebody asked you to do a mean root squared or RMS value of I of t, you just simply say, okay, I of RMS is equal to square root, same deal, 1 over t, average it from any period, any starting point to end starting point plus the period, I of t squared dt. So if so that's done. So you just square it, take an integral of it, and then the square root of it, and you get the value you're looking for. Then one thing that happens due to the nature of a sinusoidal signal, if we were told that I of t is I max times cosine omega t plus theta I, then that would basically, after you plug this whole value into this equation, it all kind of cleans up and reduces to Im over square root of 2. Sometimes you might even see this written as square root of 2 Im divided by 2 to get the square root on the bottom to the top. And of course, but we got to remember this is only valid for sinusoidal signal. And this would also be true if v of t happened to be sinusoidal. You can also get v of m over square root of 2, which can be also written as square root of 2 Vm over 2. Okay, so actually power company, most in the United States, most of the power companies, they say the voltage they deliver to your house, V is equal to 120 or 110, something like that. Let's say 110. What they're really telling you is this value is the RMS value, okay? Which is roughly, if they were giving you a DC, if they took the negative lob and brought it to the positive side on their sinusoidal signal and then kind of smushed it down so it was an even flow, it would be 110 volts. So since it's sinusoidal, if somebody asks you what is the maximum voltage that comes to your house, you can use that equation and say, oh, the maximum voltage is equal to square root of 2 times VRMS. So that value is actually what the maximum is. So if you had a scope and plug it into the wall, you're not going to see 110. You're going to see a sinusoidal signal where the maximum of the sinusoidal sign is at that point, and the minimum, of course, is the negative side of that. So that is root mean squared. So if you hear RMS now, you know what it means. The other thing we want to talk about is the total response. So if I have a sinusoidal signal, I'm going to have a total response. Actually, the best way to talk about this is take a look at an example. Let's say I have a circuit. The circuit is giving me a sinusoidal signal. And the sinusoidal signal, let's say Vs with some Vm time cosine, let's say Vm time cosine of omega t plus some phi being the phase shift. And let's say this is, we've got a switch, we've got a resistor, value R, let's say we got an inductor, although my resistors are starting to look like inductors, look like L, and they're asking us, okay, and let's say initially the switch has been open for a long time, there's no energy buildup, and at time t equal to 0, we close that. Well, we know when they close that, we can do a KVL around this loop. I is being going right like that, so we can write the equation. We can say, okay, minus Vm cosine omega t plus phi plus R times I, and we know that the voltage for an inductor is L di dt, so we say L di dt. And as we have discussed last quarter, this is basically a first order differential equation. We can solve it. I'm not going to take time here to solve it, but if we solve this thing, we will find that I of t equation for this is minus Vm divided by square root of R squared plus omega squared L squared cosine of phi minus theta, and I'm going to define theta in a minute, e to the minus R over L times t. That kind of makes sense. That's a time constant if you remember. And then plus Vm over square root of R squared plus omega squared L squared cosine of omega t plus phi minus theta. Now, again, theta, in case you were wondering what it is, theta is tangent inverse of omega L over R. Really not focused on understanding how we went from this differential equation to here. Just know that this is what you get. So this is the I of t, which is a response that is generated in the circuit once the switch is closed. Let's take a minute and look at this for a moment. What do you think is going to happen to this as the time goes by? Notice what happened as t grows. As t grows, e to the minus negative exponent is going to start growing, which means the total value of this is going to be heading to 0. Okay, this is called the transient portion. That's what This is the transient portion of the response, transient response. But look at this one. Does this go, oops, I'm sorry. Is this going to go away? This is the second term in the equation. Would that go away? But no, because this is a constant with time, and this is a sinusoidal signal. So it's going to keep going up and down over time. Simply a cosine at times increases. Every 2 pi, it's going to repeat themselves. That is called the steady state response. Okay. This one, after a few L over R, which is the time constant, after a few time constant, whatever L over R is, it's going to go away and its value is going to be 0. We, in this discussion, is very interested in the phasor domain discussion and all of that. We are very interested in the steady state, because once the switch is closed, after a moment, this is going to go away. This transient response is going to go away, so we don't care. So what we're really interested in is steady state. That's in future videos we're going to do from here. That's what we're going to focus on. This is the one term that we are there. One other thing to kind of look at as you look at the steady state response for this one, you notice that this frequency is the same as the input frequency. So response doesn't change, the frequency stays in the same frequency. There is somewhat of a shift. If you notice, there is a theta, phi minus theta. So there is some shift that occurs in the I with respect to the voltage that was put in there. So anyway, that's basically called the total response. And for this particular circuit, every time you change the circuit, of course, the equations will change and you have to go through the process. So that brings us to the end of this video. So just to recap, we talked about what if somebody tells you got a root mean square, what does that mean? In case of a sinusoidal signal, it just means the maximum over square root of 2. And the intention is to see if what would be, if you take the negative side and more or less average the negative side with the positive side, the magnitude of it is more or less, what would it look like? And squaring it and averaging it has been the easiest way to do that. That's why RMS is very popular and is being used commonly for that purpose, to show the effective value of voltage or current you're sending in. And then the other thing we talked about is if you have a circuit and you apply power to it, there is a moment in which you have a transient response in addition to the sinusoidal response, but after a few time constants, after the t gets so big, usually 3 time constant is just about when its effect goes to almost 0, and then you will focus on the steady state, and that's the subject of our future videos in the fundamentals of electrical circuits.